designing, manufacturing, installing, and maintaining the high-speed electronic computer, the largest and most complex computers ever built.
Hello, everyone. Welcome to the Building Better Systems podcast, where we explore tools and approaches that make us more effective engineers and make our software safe and reliable. My name is Joey Dodds. I'm a researcher focusing on providing assurance for industrial systems. And today we're joined by Talia Ringer. I had the opportunity to work with Talia somewhat recently. Galwa in general had the opportunity to work with Talia somewhat recently. And I thought it was really noteworthy that when I reached out to other people at the company and said, would you like the opportunity to work with Talia? A number of people jumped up and said, yes, that would be absolutely wonderful. Talia is an absolute pleasure to work with and has a really unique outlook and some really unique insights into the world of formal methods and ways that we can make formal methods research better and more accessible to a wider audience. So welcome. Thanks for joining me today.
It's a pleasure to join.
So at a high level, Talia, what is your approach to building better systems?
Yeah. So all of my work is on something called proof engineering, which are so proof engineering refers to building verified systems. So these are systems that are proven correct, and these special tools called proof assistants. So the way this works is, you'll write your program, and then you'll write some kind of specification of what it means for the program to be correct in your proof assistant. And then you'll write some kind of proof with the help of the proof assistant. The proof assistant will check this proof, and then you know that your program actually does what you said it does. This used to be it used to be really hard to write proofs in these proof assistants. People would only proof correct like really simple toy programs. But things have come really far since then. There's decades and decades of work. But one thing I noticed, looking at all of this work, is that it mostly focuses on how to prove your system correct to begin with. But one of the big problems that still exists is that, once you've proven a program correct, you're going to have to change your program. Like programs change all the time. And then, you're going to need to change all of your proofs about that program. So this can be really hard. So all of my work is on, how can I build tools that proof engineers can use to help them update their proofs almost automatically once they've made change to their programs.
Yeah, that seems incredibly valuable. We see that even, when you mention proof assistants, you are talking about systems where often users go through and sort of piece by piece manually build a proof. But even in the world where we're sort of building proofs automatically, we see a lot of challenges in having the proofs keep up with the code. And I think from what we've seen in industry, nobody wants a proof if it's going to slow down the pace at which they can update their code, at least by a significant amount. There's always some wiggle room, and everybody likes knowing that their code is correct. But definitely that's critical to allowing these proofs to be used, we'll call it in the real world, but definitely in systems that are actually in use today. And so a really critical part and sort of a bit of what I was alluding to in your unique perspective is that I feel like you've gone through a lot of effort to make sure that not only are your tools, your tools have deep technical foundations and they work, but it's not enough to have them work. They need to actually work for the people that are using them. Can you tell me a bit about that?
Yeah. Ultimately, my tools are supposed to serve proof engineers. So if I don't have input from proof engineers, then I don't know if I've built a tool that can actually be used for anything. It might be theoretically interesting, but in the end, like, what does it matter? I think I actually did this a little bit too late. Working with Val, with someone at Galwa, and having him like really use my tool and give me input, and then I would make changes to adjust to that input. I think that's been one of the most interesting experiences for me, because I think the things that users want in your tool are not always things that you would think of. You're so used to using your tool, you know the inside of it. You might know how to avoid problems just intuitively that a user might be, afraid to do. So I feel like by partnering with someone, it's been really nice to see what those problems are and be able to address them and make the tool more usable. I wish I'd done that earlier, honestly.
I mean, on one hand, it would have been great to do it earlier. On the other hand, you did it at all, right? And it's not like it's not easy as a researcher to just like email people and be like, "Hey, do you want to work with me?" How have you found the response when you go to do that in general?
I think a lot of people are interested in helping. I think it helps a bit that my target audience are proof engineers who are generally just interested in contributing back to the research world in some way. So when I reach out with like, hey, I have this tool, it's kind of a prototype, I'd like to give back to you, in the future, but it might not give back to you immediately. I think people um, are really willing to get involved in that process, not just because they want my help, but because they want to help me as well. Yeah, I think it was a little nerve wracking doing that, reaching out. I think this is the main reason I delayed it for so long. Um, like, so one of the professors at UW, Zach Tatlock, at one point he told me that like, one of the big tests of success is like, um, having people actually use your tools. I think this has been echoed by my advisor. A lot of people believe this. Um, I think it's true, but there's like a confidence aspect to that too. Like, if you build a really good tool and you're too afraid to reach out and be like, hey, try to use this tool, let me know how it's going, let me improve it, then you'll never know if it's a good tool. And it could be a really good tool. And I think I was surprised that like by the time I reached out, the tool was already working very well. And I think I just lacked the confidence for months to reach out and ask someone.
Yeah, I mean, and the other side of that is like sometimes, and this has happened. This has happened to me. Is sometimes your tool is bad, like, but it's at some point it's better to know. Like at some point, like it makes it hard, no question. Like the doubt that your tool might not be what you think it is, or that it might not work the way you think it is makes it like really hard to reach out. But having received that feedback, like this tool isn't ready for us this year. Like this tool isn't where it needs to be for us to use it. It gives you something to go after, right? And at least like at least my error messages aren't good enough. This is too stressful to use, like because in some sense, having received that feedback, sometimes the doubt and uncertainty is worse than the certainty, and like having a concrete thing to address can be really nice. So I think it's great that you took that step because, like, a lot of people, especially in grad school, but even researchers are not taking that step very often. And we write things in our papers like people should use this in this way, or this will make software better in this way. And then there's this necessary step, or about like actually doing something to get that in people's hands. Um, so is this something that given how hard it was, is this just something you believed in? Is that why you went after it in this way?
Um, I think it was actually like encouragement from my advisor and from others at University of Washington. I think this is a big difference in how University of Washington approaches research from some of the other universities that I've seen, which is like especially our group, our programming languages group, um, seems very focused in building systems people use, not just prototypes that you build for a paper and then throw away, um, which I think is important because in a lot of our area uh, we don't really have there are still a lot of areas where we don't have like good metrics for like what it means to build a good system. Like even figuring out what those metrics should be is an open problem. to some degree. There's obviously like a ton of research in software engineering on this, but I think some of these questions are still open, especially when you get to like proof engineering. I think with that in mind, like while we're working on finding out those metrics, we also need ways of measuring success, and having people use your tools is one of those.
Yeah, definitely. And having people use your tools, metrics are great, but they also pose risks in terms of the things that you choose to optimize can get heavily guided by your metrics. And while user feedback is softer, it's also very useful in that you get to just sort of see directly what people are thinking, and you can you don't have as many bad traps to fall into there. As a side note, every time I hear cool things about University of Washington, I get a little jealous, because I actually applied to University of Washington as basically my top choice, and it didn't work out for me. So
it's all random to some degree.
It is. It is. But
where did you go again?
Well, I ended up at Princeton, but
okay.
It worked out. It worked out fine. Yeah, so that's really cool. And then I think again, like the other thing that I missed out on, frankly, as a grad student, that I think you're getting a lot of is just like talking to more people, which again is hard to do, but I assume has been pretty beneficial.
Yeah. What do you mean by talking to other people?
Well, so much of our world is, and well, I mean, this is not like uncommon to business or academia or whatever, but so much of that is about making connections, but it's really hard to do it.
Oh yeah.
It's really hard to just talk to people. It's something I've gotten quite a bit better at since then. And part of it is just this, it's the same sort of idea with building tools. Is they're gonna be like, no, I don't want to talk to you. You're not good. But most people are like, oh, I'd love to talk to you.
Yeah.
And it's great. And at worst, they're like, I'd like to, but not right now. And that's not that bad. But I've never reached out to someone, maybe you get silence, but I've never reached out to someone and been like, no, because I'm not going to do that because you're not good.
Yeah.
Right. It's not a response, but in your head, it's a response.
Yeah. I remember I think the switch for me there, the thing that made me able to do that really easily was in my first year of grad school, I went to a conference. I went to talk to him about my work, and I was so worried that he'd be like, oh, that research project is garbage or something like that. Instead, both he and everyone else I spoke to was like, oh, wow, you're already doing a project. I was like, okay, expectations are set pretty appropriately. So now I just reach out kind of unabashedly, but it's still really scary for me to claim that my tool is good.
Yeah, well, I think successful researchers and successful developers, we'll go as far as saying successful people, always find it hard to say that they're good enough, because part of that is definitely about you always want to find the next thing and do better at it. And it's not a bad thing, but you definitely have to control it, right? It can get out of hand. I'm sure a lot of us know about how that can get out of hand. So let's go into a little more detail about the kinds of things with your research. You mentioned updating proofs. Can we talk a little about the kinds of things that might need to be updated, and maybe what some of the challenges there are?
Let's see. So I can give some big examples, but a lot of these are still too hard for significant automation, but they're ongoing challenges. They're sort of the driver of the kind of work I do. One example might be, so there's a verified operating system that's been proven secure, but it's been proven secure on one hardware architecture. And people would love to be able to prove it, to take those proofs and sort of adapt them to all these different hardware architectures. But this is really hard. The thing you're proving changes a little bit. The proofs you write have to change to adapt to this. So every time you do this, you'd have to change all of these proofs. So that's sort of one of the big driving examples. Might be updating proofs of something like an operating system to adapt to new hardware. Smaller examples might just be something like you have a verified system, it uses some library. Like the proof assistant language that we use has like a standard library. The standard library will have not just functions and stuff that you can call, it will also have proofs about those functions. And you can use those. You can refer to those theorems inside of your own proof. But sometimes, they'll change when they're updating the language. They'll change the standard library. They'll change one of their specifications, and then this will break like everyone's proof development. And there were a couple examples already where we were able to look at just changes that occurred inside of the library and use those to automatically fix proofs at the client level, which is pretty powerful.
Yeah, I mean, honestly, like even this is a problem that every software engineer is familiar with, right? The idea that a standard library could, deprecate your function, then eventually remove it, and then all of a sudden your code's not going to work. And like the idea of in that setting, the idea of occasionally being able to go through and fix things automatically is really meaningful. So in the proof world, I think it's maybe even more impressive, but hard to say. I guess you have some stronger frameworks to work in, I guess, in the proof world. Sometimes it's more clear what you're trying to do.
Yeah, that's the big thing. Like it's both harder and easier, I would say. And it's harder because you have not just functions but also proofs that you need to fix. But then I think it's easier in that one of the biggest challenges in program repair, in automatically fixing your programs when something is broken, is that you don't know when you're correct. And so you often need some additional information. Test suites tend not to be enough. So you might use examples, like have the user make a couple fixes themselves, or you might write a specification. But in this world of proofs, we already have these specifications.
Right.
So we're just we're able to totally work around this problem. Like we know exactly when we're right, and that's really nice.
Although you do sometimes end up in a situation, I guess, where you're not clear whether the specification needs to change or whether it can stay the same, right? That's if we're talking about proofs that match code, and the code changes, then the specification sometimes just becomes wrong by nature of the proof changing.
Yeah, that's true. I think there are a couple ways around this, which is like either you can have some human in the loop, like hey, is this the right way to change the specification? Or you let them change the specification themselves. Or sometimes you have sort of like well-defined ways of changing your specification that have some sort of guarantee that like, yes, the specification has changed, but it's changed in a way that only reflects this change somewhere else. And, modulo that change, it's the same, essentially.
Right.
Yeah.
Yeah, I really like this idea of human in the loop with proof tools, because I think it's the answer to making that experience pleasant is, I think, challenging. And you're doing kind of like the light version of this with just having people use your tools, but like there's UX people exist, and it would be lovely to see some closer interactions between proof engineering people and UX people, because I think that a lot of really good work could come of that. But it's not something that I've seen. It's something I think to aspire to, probably. Yeah, and again, that UX story is key, I think, there, and like figuring out what to ask is so hard, I think.
Yeah.
Because I think it feels like if you can ask the right question, you could actually get it. What I think I view as kind of the ideal end point for this is where a proof engineer can write a proof once, but then from there we can ask good enough questions about how to update it that a software engineer could maintain it. I think that would be an incredible place to end up, because it's one of the big questions when we write proofs is like, how do we keep this proof going? How do we keep it alive? And there's only so many there's only so many people that could or want to be proof engineers today, at least.
Yeah.
And so, and there's a lot of people that want to be software engineers. So it would be great to put that in their hands and let them, and let them use the tools. Cause I think software engineers see a ton of benefit from this, right? Like, who wouldn't want to answer 4 questions and then say like, oh yeah, like your code's correct. Like you did it. Like go home and and sleep all night without worrying about whether it's going to crash your, your production server or something.
Yeah. I would really love to see proof engineering just merge back with software engineering at some point. Like, I want proofs at some point to be as accessible as writing tests. Like, we don't think of a lot of places, most places, I think, like when I was at Amazon, for sure, you were expected to write your own test for your code. It's not like you write your code and then you just give it to someone and they do all the testing. We did have people doing extra testing, but I think I would really love to see, not for all programs you could ever write, because it doesn't make sense to prove correct every single program you would ever write, but especially for like more critical programs, it'd be nice for software engineers to just be able to write and maintain them.
And we've seen this kind of thing happen with other fields, right? Like even when I was in school, there was, it still is a field, but like systems as a field used to be like a thing. And now if you like talk to people at Google or Microsoft, they're like, why is that a research field? That's what we do. Like, we figure out how to do protocols like day to day. And so, having that as a research field, like, yeah, there's still ground to be made, but also everybody's doing that. Everybody, like, nobody's building a monolithic system anymore, right? Everybody's building systems that are talking to tons of other systems. So that there are like definitely inspiring stories of research fields just spreading out so much that they're like barely a research field anymore, and that everybody's doing them. And yeah, for like formal methods becoming that would be incredible. If the two of us can see that in our careers, I think that would be just a great thing. Recently, you reached out and did a user study for users of these proof assistants. Can you tell me a bit about that?
Yeah, so this was a user study of the particular proof assistant that my work is focused on. Essentially, what we did was we worked with a group of, I think there were like 8 people in the end. They were all intermediate through expert proof engineers. And we actually listened in on their entire development process, with their permission, obviously, for a whole month. So we had a server set up, and we built this tool that would, it just instrumented the proof assistant they were using. And every time they made any kind of change to a program or to a proof, it would send that over to the server, record that change as they went. So very, very granular. You can replay the entire process of development. And our goal was to figure out, how are the proof engineers changing their programs and their proofs? What kinds of changes are they making? What is it, and after they make those changes, how are they changing their proofs? So yeah, this was published in January, I believe. And it was a lot of fun. I don't know.
It sounds like it sounds like you would get so much data, it would be incredibly overwhelming. How did you tackle that problem?
That's definitely true. I think one thing that helped is that we spent a lot of time building scripts to process the data. So one thing I did was I wanted to be able to look at the way that people were changing, changing data types, essentially. And looking at this raw data, this is crazy impossible. But instead what I did was I just have a Git repository. It's actually public. And then every time they made one of these changes, it would just have a Git commit. So then you can go in and you can look at the diffs, and you can see, what sort of things they've changed. Now it was still a little bit hard. If you step down in your IDE and you write some data type, then you step up and you change something, and then you step back down. Each of these is going to be considered a change, and you might have to look not at the difference between commit 2 and commit 3. You might have to look at the difference between commit 1 and commit 3, or so this part still involved way more human effort than I would have liked. I think automating it more would be fantastic. But I did, after I did all that sort of manual part of the effort, I did save all the commits, link to them in the repository. So the person who's using the data doesn't have to go and look through those.
And was your objective for this to just understand, was this linked into your research basically? Was the objective of this to understand how people are using these tools so you could understand how to help them?
Yeah, essentially. So it was a partnership with Alex Sanchez-Stern at UCSD. And he also builds proof engineering tools. His tools are they focus on something different from mine. But both of us were interested in really similar questions about what kinds of mistakes people are making, how they're fixing them, and how can we build proof engineering tools that help them do that. So yeah.
So an approach to proofs that update automatically with changing code that we use quite a bit is SMT solvers. And if you're not familiar with SMT solvers, I know you are, but if listeners are not, they're basically, you can kind of think of them as little math engines where you give them a math problem and they tell you if they can solve them or not. So you'll give it an equation with some number of variables that it needs to figure out, and it'll tell you sort of if it can figure out variables or not. So is that a direction you've looked at for your research, or have you found that it doesn't necessarily provide a lot of additional value for the kind of work that you're doing?
That's an interesting question. So I think SMT solvers, there's some work on using these from within proof assistance. You run into some fundamental problems where SMT solvers use essentially a language that's just fundamentally different from the one that we're working in, and you can't fully translate everything from our language into a world where you can use SMT, but sometimes you can. And I think for those problems, you often don't need that sort of heavy automation to change things for you, because you can just use these built-in proof strategies. You can use the automation that already exists to dispatch them for you. But that doesn't always work. Now, I think there's some really promising work right now, and I have a lot of ideas for this, on taking some of the things that SMT solvers do on these different languages and actually changing them into ways that will work for this kind of language. And there are some fundamental questions there, but I think this hooks in really nicely to what I'm doing.
Right. So what you're saying is SMT solvers are great, but we're not going to be able to just directly ask them the questions that we have, right? We're going to have to be a little clever and ask them questions that they know how to answer, but they are really good at answering the right kind of question, basically. So figuring out how to take these complicated goals and turn them into something they can deal with? Or are you talking about writing something that's like an SMT solver but completely different?
Yeah, actually like an SMT solver but different.
Interesting.
Yeah, like using the core algorithms that make up an SMT solver, the core data structures underneath these. I think you can take them and tweak them. And actually, so Leo De Mora, who's at Microsoft Research, has done this for one particular language. It's a little different from the one that I'm working in. And this is one of the reasons why their proof assistant lean, I think, has become pretty successful. But I think you can do this more generally for the kinds of changes that I'm interested in, languages that I care about. And I think that will add a lot of power. So yeah, this is something I'm really excited about. I wanted to do it before I graduated, but it's just too much of a time constraint. So this is going to be something I really want to work on as junior faculty. Yeah.
Yeah, no, that sounds like an incredibly promising problem. This is kind of one of these things that's like it's obviously people want this in its best form, right? Like C has for some reason C has type annotations where you can actually like say I'm taking an array of this length, right? That's a thing you can say in C. It's going to completely ignore that and say this is an array of whatever size, if we want, and more like even worse, you can't figure out what it actually is if I've given it to you. But like people write these annotations that say like I'm taking an array of length 5, right? And that's not hard that idea is not hard to understand.
Yeah.
It's it's very hard to understand that the programming language doesn't care if you wrote that or not. But that's a separate problem. So like yeah, like again, yeah, like once this usability story is figured out, like again, I don't think people are going to have trouble saying like, and maybe it's harder when you make it a variable. So like maybe it's harder for people to think about this is a function that takes an array of length n and returns an array of length n plus one, but that doesn't seem that complicated in most cases. And it's again just the details of making sure that the computer understands that is the hard part. And if there's like a promising story for automation there, even in like a lot of the cases, right? I think that could go a long way towards hopefully not just being useful in this proof assistant world, but being useful in, C is maybe a dream, but like we could talk about something like, we could talk about something like Haskell, which is like a bit more mainstream, or even like Java has, I think that the story is a little easier with Java.
Yeah, I think it will be a lot of the same kind of flow we were talking about earlier, like asking the right questions. Like I think you'll be able to say like, array of length 5 and it'll be like, I can almost prove this, but like I need you to help me out here a little bit. Then you answer it and then it will be able to check that for you.
Yeah, and even the world of even the world of static analysis recently has shown us that like even if you don't always say yes, it's always length 5, but if you say no, this is definitely not length 5, that's actually like enough motivation for people to go ahead and use it, right? And that world is, the static analysis world has really taken off where it's like you don't have to guarantee me the absence of bugs, but if you can tell me when there's definitely a bug, I'm always like and do it quickly, I'm going to be really happy with your tool. Because that's any one of those, like anytime you can concretely say like here's a bug for sure, fix this, like that saves developers so much time. So that's all the time we have. Thanks a lot for joining me, Talia.
Yeah, it was wonderful.